Linear regression is a statistical technique that allows us to predict the value of a dependent variable from one or more independent variables.
Let's suppose that we have a shoe factory. And in this factory there are a number of shoemakers who have varying amounts of experience. Their experience making shoes is designated by the x-axis here, and the amount of money coming in, the amount that's charged to make each pair of shoes, is designated by the y-axis here. So let's say we have someone who's a new shoemaker who's been working for about a year, and this individual makes shoes of such quality or of a level of quality that the factory can charge $30 a pair for these shoes. So we would have a data point here at the intersection of experience and price of the shoe. Let's say we have other shoemakers in the same factory who have much more experience. Let's say this represents 4 years of experience. Because of the additional knowledge, skills, technique that this person has, then they might be able to charge much more. Let's say twice as much, $50 for a pair of shoes. So that data point would be here. So the idea is, if we have a set of data points that represent some bivariate relationship, in this case, between experience on the y-axis, experience on the x-axis, and then the cost or the price of shoes on the y-axis. So we end up with a cloud of data points. So one straightforward analysis that one could do as a starting point is to try and find some correlation between these, and I won't go into the mathematics, but there are a number of well-known orthodox approaches to finding correlation between two different points. Linear regression sort of takes that to an additional stage. Using a mathematical technique called sum of squares, which I'm not going to go into detail on, it's possible to calculate what's called the line of best fit. And this line represents the mathematical mid-range, so to speak, the mathematical line or slope on this graph that best represents the overall value of all of these different data points. So the value of having this line then is, if there are areas on the graph, if we extrapolate, which is looking at ranges, values beyond the data that we have, or if we want to interpolate, which is trying to find values within the data set or between values that are actually known. By determining this line of best fit, also known as a regression line, this allows us to make predictions on, in this case, two variables based on with some amount of probability. So, for example, if I wanted to find out for this much, given this much experience, what would I expect to be able to charge for this pair of shoes, the regression line lets us make an estimate. And we would know with some amount of probability, which we would measure using r squared, which is the coefficient of determination. More on that in a second. And this r squared value would let us know, okay, with this amount of likelihood, given this much value for this variable, the value for this other variable, in this case this would be considered the dependent variable, the value would be this much. Now, in this previous example, we only had two different variables, right? We had one independent variable on the x-axis and one dependent variable on the y-axis. In reality, it's often the case that even given one dependent variable, which I'm going to call y, we may actually have multiple independent variables that we hypothesize might be necessary in order for us to make a good prediction. So this is where the formula for linear regression comes in. The formula is y equals beta, so this is the character beta, not the letter b. Beta naught plus some number of beta coefficients plus an error term. So to break this down, y is going to be the dependent variable. Let's say we're trying to figure out GPA. We want to predict the GPA of college students. Beta sub 0 or beta naught is just kind of a mathematical artifact. It's the point on a graph where a line crosses over the axes of the graph. In this case, I've visualized it as passing through the y-axis, but it could just as easily pass through the x-axis as in this example. So y equals beta naught plus this, within these brackets, the representation, the visualization is meant to indicate what are called coefficients. So these coefficients are the independent variables that we're plugging into this formula because we feel that they have some influence, some impact, some predictive ability on the dependent variable. If you've ever seen an academic study or seen a news report about an academic study where the research authors or the journalist who's reviewing the research says something like, researchers have found that diet has a bigger influence on cancer than genetics, which is obviously an example I'm totally making up, but that would be an example of ultimately a linear regression analysis, because in this case, diet and genetics, however we would operationalize or define those, would be independent variables that we would plug into here. So in this case, they would be, we start with beta sub 0 in order to get the start of our slope of our regression line. And if we had two independent variables, let's say, again, diet and genetics, let's say genetic predisposition to cancer, these would be two independent variables. So we would have diet, let's call that beta sub 1, and genetics, let's call that beta sub 2. So in this case, our formula would have two values here, one for diet, one for genetics. We could have 3, we could have 5, and I'll give a specific example shortly. But the point to take away is that what's key here is that by going through the mathematics, which I will not explain in detail, we're able to get an idea with some degree of probability of how these various independent variables help us predict the value of the dependent variable, specifically by helping us establish the amount of variance explained by this string of coefficients. And then finally, one last point before I go to a specific example. This is meant to be the lowercase Greek letter sigma, and sigma here just represents what we call the error term. Error term just means the randomness, or as we say in statistics, the stochastic element. So this is just representing the degree of uncertainty. You can think of it as the rough equivalent of an error band or margin of error in a survey, for example. So to look at a real example, let's say, or a more concrete example, let's say the research question I have is trying to predict or determine the cumulative GPA of a set of students, and I've determined, after going through my analysis, my preliminary analysis, that there are two variables, two coefficients, two independent variables that, taken together, explain a sufficient amount of variance. So I'm glossing over the model building process where we determine exactly how many coefficients, how many independent variables are we going to care about. But let's say I've gone through that process and I've determined that I care about two variables. So again, to translate this, the cumulative GPA is what I'm trying to predict or determine. That would be the dependent variable. Beta sub 0 is, again, just the point where a line crosses over the axis. Beta sub 1, let's say, is my first independent variable, and let's say that that's SAT score. And then beta sub 2, let's say that's my second independent variable, and I'm going to say that that's number of college credits. I should point out here that in order for this to work mathematically, these independent variables on this side of the equation must be either continuous variables. So, for example, an SAT score obviously is a continuous value. It can go from some minimum to some maximum, but it's not ordinal. It's not first, second, third. It's not nominal. It's not just labels or categories like you might have in some personality tests, for example. It is a continuous numeric value. So independent variables here used for regression analysis must be continuous or dichotomous, which means a binary value, so 0 or 1, yes or no. In my example, to keep it simple, obviously SAT score, continuous variable, number of college credits, and let's say I'm assuming this is college credits a student had coming into the university from AP exams, dual enrollment, what have you. Obviously that would be a continuous variable because it can go from 0, no prior credit, to infinity. And then finally the error term. So I've, again, having gone through the process of determining that this was the best model to use, and I of course have not gone through that process in this video, but we get to this point. So what does this actually mean in practical terms? So the whole point of a linear regression equation is to help us make a prediction. So again, if cumulative GPA is the dependent variable that we're trying to make a prediction about, having gone through the mathematics, which again I'm skipping over and not describing in this detail, specifically what comes out of this analysis are coefficients. These coefficients are numerical values that then we can plug into the individual student profile or record to help us predict the GPA. So let's say I've gone through the math and I find that the value of beta sub 0 is 2.5. And this is a specific outcome, a specific value I would have found by going through this process. And recall in my fictional example here we had two independent variables. So let's say the coefficient that I've calculated for beta sub 1 is 2, and then the coefficient for beta sub 2, my second independent variable, is 3, and then the value of my error term, or sigma, the random element here, is 4. So what I have here then is an equation that lets me predict the cumulative GPA of a student based on the value or the outcome of 2.5, the beta sub 0, the interception point of that, the beginning of that line of slope, 2.5 plus 2 times beta sub 1, and again we said that this was SAT score for a student, plus 3 times beta sub 2, and we said this was number of credits, plus 4, which was this error term, the random element. So let's say we have a student with an SAT score of 900 and with 12 credits coming into college. To predict his cumulative GPA with some known degree of probability, which would be represented by R squared, which I'm not making up an R squared for this model, but let's say that it was an R squared value. It was a degree of certainty that we were comfortable with. We predict this GPA then by taking all these coefficients, multiplying them by the specific value for a student as appropriate, as necessary, and then coming up with a number. So for this student with an SAT of 900 and with 12 credits coming into the university, their cumulative GPA with some likelihood, with some probability, not 100%, but also not 0. This student's cumulative GPA we would predict to equal, in this example, 2.5 plus 2 times 900 plus 3 times 12 plus 4. Now, in reality, these numbers are nonsensical because the GPA would be like a 5-digit, a 3-digit, 2 or 3-digit number, which is not reality. In reality, the coefficients would probably be values below 1, more likely than not. But again, this is not meant to make mathematical sense. It's just meant to illustrate the general idea of linear regression and what that tells us. So again, to review, we want to determine or predict with some degree of certainty, or if you prefer, some degree of uncertainty, a dependent value, in this example, cumulative GPA. Going through this regression analysis process, we're able to determine these coefficients as well as the model that helps us explain the most amount of variance while still remaining parsimonious. We get coefficient values that are output from this process that allow us then to plug in numbers for individual students that take the place of these different variables and then help us arrive at a specific prediction, in this case for cumulative GPA. Now, final note, and this is to sort of wrap up by talking about this concept of R squared, of variance. The value of R squared can vary from 0 to 1. So an R squared of 0 means that a given model explains none of the variance that would be found within the dependent variable that you care about, and a value of 1 implies a model that 100% completely accounts for all the variance. In reality, we're always going to end up somewhere in between these two values, because hypothetically we could create a linear regression model that has an infinite number of independent variables that we can plug in. But just conceptually, this becomes very difficult to deal with, because if we want to make a calculation to predict, let's say, student GPA in our example, if we had to consider 20 variables, 30 variables, 40 variables, besides the fact that that is just difficult to do in practical terms, in terms of the analysis, we have to gather all that data, create the process for making the calculations. Of course, we reach a point where there are diminishing returns, where adding additional variables might start accounting for such a small amount of variance that the model becomes clunky. So it's important to be parsimonious. Again, obviously parsimony is just the concept that an explanation for a phenomenon, or specifically in our case, linear regression model, is best when it's as simple as possible to explain in general terms, or to model in general terms, the phenomenon being investigated. Or to put it another way, we could have an infinite number of independent variables to describe some phenomenon, in this case to help us predict the cumulative GPA. But what does that really do for us? If we had to worry about an infinite number of variables, then it's easy to get overwhelmed. So sort of the whole point of linear regression is to try and find a balance. You want to have enough variables to account for a decent amount of variance of R squared, and what equals a decent amount varies from field to field, but my own view, and a lot of other psychological scientists would say, if you can get better than chance, so an R squared of 0.5 or above, you're doing pretty well. I think the top studies that are seen as very, very successful with very, very compelling findings, they have an R squared that hovers around 0.7. So that's sort of the threshold, I would argue, 0.6, 0.7 for a model that is fairly good, because you're above chance, above 0.50, above 0.5. It's better than flipping a coin. You're not going to have complete certainty, but you'll be better than just than flipping a coin. So you'll have a situation where you're trying to balance, again, given what you want to predict, given the amount of uncertainty or certainty, depending on how you look at it, that you find acceptable, and then this idea of parsimony, of having an efficient explanation with just enough variables to help you determine what you want to determine, but not so many variables that the whole structure becomes unwieldy. Exactly how many independent variables, how many coefficients do you want to drop into this equation? How many beta values? And the answer, of course, will always depend on the specific research question, the specific situation. But it is somewhat subjective. One can't get away from that. And yet, nonetheless, there is a methodology here that, if nothing else, at least is fairly easy to comprehend for someone that has basic training in statistics.
That concludes my presentation. I hope this general overview has been helpful for you. Please let me know if you have any questions.